Hello viewers, welcome back. Is Abdul Babatane Bukola again for Numbera Process Designers. So I am back again today on another introductory video to Aspen Custom Modeler software. I'm going to be introducing you guys to the software to how to I'll be explaining how to use the software to create custom models for beginners, especially those that have not used the software before. So I am going to be introducing you to I'll be creating a simulation of a small unit operation like a mixer, just to introduce you guys to the software. So I'll be explaining the modeling language and what we use the software to do in process design and simulation, and the analysis to and everything that is fundamental about the software will be explained in this video. So stay tuned. So the first section is about the software. The Aspen Custom Modeler is a process modeling software developed by Aspen Tech, and it is designed or used to create custom unit operation and detailed engineering models for chemical process and something that is similar to that are not covered in standard simulation software like Aspen Plus and Aspen ICs. So you have the luxury of creating your own model from the basic mathematical modeling equation for the system. You just have to interpret the modeling equation into programming language that is used in the software, which is very straightforward. I'll be explaining to you today, and they are going to use it to create the model that you can use in Aspen Custom Modeler, or you can integrate with other models in Aspen Plus or Aspen ICs. So the software is to use the software, you purchase a license for the software with Aspen Plus or Aspen ICs, and you buy the software from the Aspen Tech website. So and once you install it, you can use it to create your model. So so here is the software interface. Once you install the Aspen Tech software, you have the software uh, part of the pack. Then you can open it by searching the Aspen Custom Modeler in the search bar. Then you open the software. So in the software, there are different areas in the interfaces. I'll be explaining the software interface over here. So there are different areas in the software interface. We have the Explorer. This is the Explorer area. This is the flow sheet window, where you are going to be, if you are familiar with Aspen Plus or Aspen IC, this is where you are going to be defining the model system, simulation model system. You are going to be connecting the process flow diagram of the chemical process. Then you can model it. Then we have this is the library, the model palette, something like the model palette. Then we have the ribbon. So then there are some other pages on the website, but this is actually the basic interface. You can see write create the windows. We call it windows here to be rearranged in any ways that you want. You understand? You can add some new windows to it. So but I will be explaining what each of the interface is used for. This is like the navigation area where you can navigate from one section to another from the software. You have the component list. In this software, the property environment and the simulation environment, there is no difference between them. You understand? So you define your components in the component list. So in order to define your components, you can create, like I said, this is basically for custom modeling. So you have the luxury of creating your own custom model that is not even from the Aspen database, or you can do a simulation that doesn't even use chemical component list. So there is a lot of power that you can that you have in modeling for when you are using the software. So, and for example, I'm going to create a like a salt water mixture for my component. So to do that, you go to configure environment. So like if you don't want to use component, you configure properties. So if you don't want to use component, you can use do not use properties or use custom properties. Then you can go to using Aspen property system, because I want Aspen properties to define the all I call it the property system of the chemical system that I'm trying to model, like the all the data bank property that is inside of the component will be exported to Aspen Custom Modeler. So I'll be using it to calculate some properties for the system. So if you have some Aspen property file for the chemical system, you can import it or you can edit a new one by creating a new property system for your chemical system. So this is a property. So I'm going to define H2 and NaCl as my components for the simple simulation that I'm trying to do, for example. And the property method that I'm going to be using for the system will be electrolyte NaCl. Then I can select the property. So with this, I've set up the property system in Aspen Plus that will be exported to Aspen Custom Modeler when I start the simulation. So you save it, then you close it. Then the file will be recorded in Aspen Custom Modeler. So for the simulation, you have it embedded. It has been configured using embedded Aspen properties. So now you have set up your property environment in Aspen Custom Modeler. Then you need to define the property that you want to use from the property that I've connected to the embedded in the Aspen Custom Modeler file. So I'm using the two components. So I'll pick the two components and I can edit some of the property, like using some other fluid package that is available, or the property model that is available, or method, let's say property method that is available in Aspen Custom Modeler. You can see the one for waters and the likes and all these kind of things. So I'm going to select this electrolyte NaCl. Then you can change the one for free water. You can see system TL, enrich component. If you have any component in the property file, you can select them and click OK. Then you can see add a mini component list. So the one that you have in this default is the default component list. That is the universal component list for the whole simulation. You can have a subset of them as we are working on the simulation. So this is for global, when you are defining global tables or forms for the simulation. And you have the flow sheet area where you can, because like I said, it's a custom model, you can create some code for the flow sheet. So there are some kind of modeling that you can, maybe you add a constraint to some equation in the flow sheet, some variables in the flow sheet, or some parameters in the flow sheet. This is where to do that. So now, not to make this video long, I'm going to create this is custom modeling. This is the main deal about the software. This is where you create the custom models that you are going to be using in the software. Like you can create different kinds of model that you have in mind, like electrolyzer, like fuel cell, like pipeline, like custom equipment that you have in the plant, like power plants, any kind of thing that you can think of if you understand it. Even like a cost model, you can create a costing model in Aspen Custom Modeler. You understand? Then you can get any kind of like metallurgical system, drainage, different kind of model that you have in mind. So you can create them in Aspen Custom Modeler in this custom model page. So and you have the libraries. Libraries are predefined model that's inside the software, because you don't have to create everything, like streams, like dynamic. All this model that you are seeing, they are for dynamic model. You understand? So you can go to some other models that you have here. This one are hierarchy for soft flow sheets. Then you can go to this place. Just give me a minute. You can see some kind of ports that you have. Ports is like a subset of a simulation model. You can see some procedure, some structures, and some models that have been in the software that you can use in your model that has been defined to aid you as you are creating your complex model. So, and you have stream type. There are different kind of stream. You have collection, control stream, heat stream, material stream. You can use them in your simulation or in your models that you have created in the custom modeling. So then you have some system library, that those are another kind of models too that is available. So you have the models like distribution, domain, hierarchy. You have parameters type, angle parameter, logical procedures. You have port type. You have stream type that are in the systems of the simulation, and you have variable type like real variable, slack variable, and the like that you can use. So in order to use this software, you have to have some programming background to use the software. So, and like I said, this is the interface. This is where you create the flow sheets, and these are the some of the tools. You pick some of the tools. You can navigate from one window to another with this window tab. You can see help about the software in this ribbon, like Aspen Custom Modeler help to read more about the software, about the tools inside the software. So this is very, very, very important, essential in understanding how to use the software. So, and we have um we have a lot of documentation on the software here, so you can easily move from one section to another to understand different areas of the software. So and moving forward, the modeling language. Yeah, so in order to use the software, the modeling language is an equation oriented modeling language, or you can even say object oriented modeling language. That is, like the model is by model, like each model is like a system on its own. Then you can have the property of that object, and which you can do some operation on as you are doing the you are writing the code, and you can use to perform some operation, and you can do some calculation on. Then that object is also another subset of another object. So whenever you want to refer to the sub object, you have to put the name of the parent object in, just like the hierarchical modeling approach. Then you have some hierarchies, some sub flow sheet inside another flow sheet. You understand? Then when you want to refer to the total the any child object, you have to refer to the parent object too. You understand? So and it uses Microsoft Visual Basic scripts for when you are writing some commands for the to perform some operation inside the model, for scripts in the model. So that is the modeling language. So in order to demonstrate some of the modeling language, I'm going to create a custom model in the custom a simple custom model in the custom model that I call that is a mixer. So once you create a mixer model, it will show you to it will create it will show you the editor page, which is where you it's just like your code editor. So for the code, this is what will really help you to create the code. You have the model that you define as your object, which is the mixer, and this is the end of its code. So inside the model, you define the parameters to be used in the model, the variables to be used, the any submodel that you want to use, following this syntax that is structured. So this is the syntax of the code. Then the ports. So all this area, they are like the declaration area of the code. Then you have the equation. The equations are the modeling mathematical models for the models. You understand? Like the formula that you use to do the fundamental equation that controls the model. Then if you want to calculate some properties, then this is the syntax for calling the properties. So you can see the equation name, the expression on the left hand side, and the expression on the right hand side. So then you have the name of the property that you want to call, the procedure name, and the argument of the property. Then you have the variable type, the parameter type, the model type, the structure, the port type, and the likes. So for this model, the port is a model that carries information from, if it is input port, it carries information from outside, from another model into the model. While if it is output port, it carries information from the port, from the models to the outside model. And that information can be anything, can be results like flow rate, like temperature, like any kind of thing that you are looking for when you are doing the simulation. So that, like any kind of property or information about the model that you are calculating with the simulation. So for example, you are working with a mixer, so we'll define two ports. We have to define the inlet port and the output port. So I'm going to put double slash for comment. So I'm going to say port declaration, port declaration. Then for my input port, I can use a tool that is very handy in defining, in writing code in the model editor, so which is the model assistant. So I'm going to write the name of my ports, input ports here, 1. Then I can put the type of the input port to be a mole fraction port. Is a special kind of port type that gives you some information about the kind of information that you want inside the port that will be transferred from one area to another. So for mole fraction port, you transfer the mole flow rate, the molar fraction, and the temperature, the pressure, the enthalpy, and the molar volume. Those are the information that is transferred in between the ports. Then I can insert it like this. Then I can write another one for import port 2, insert that one too. So let me call it output. Okay, output is actually an internal name, so I'll call it outlet. Outlet. So I can call it output port mole fraction type. So I've defined a port to carry information, inlet and outlet of the model. The next thing is to write the variables to define some variables and parameters of the model. So for the variables and parameters, we have the flows that will be flowing through the inlet and the outlet. So we are going to hold another flow, we define another flow to hold the total flow of both the inlets. Then that will be recorded as the total flow out from the material balance constraint, and the mole fraction of any component that is coming through the two inlets of the mixer. So for this mole flow, that will be the variable, and it is defined as a flow mole variable type. Is a form of variable or molar flow rate from for that is defined in the, if you check this place, you see the flow mole variable in the custom modeling. Check the variable type. Okay, think is in modeler. You go to modeler, so you see the flow mole variable type that has been defined there to be this. This is starting from 0 and descending from 1 used per 10, and the unit is given in kilomole per hour. Are you with me? So then we have this mole fraction as a mole fraction variable that is also there. So, and you have the upper limit and lower limit of the variable. Then we start writing the equation. This is the equation that I defined using the Aspen custom modeling language. the equation is written as this, and you have the total mass flow. The M flow is equal to inlet flow rates, the first inlet and the second inlet flow rates. This F is like the object, the flow rate object, and it's under the inlet port. So it is part of the object inside the inlet port. It represents the flow rate, the molar flow rate of the port, any stream that's connected to the port. So then the summation of the two flow will give us the molar flow rate. Then for the mass balance, component mass balance, the mole flow, component mole flow of each of the component is equal to the total mole flow that is summed up for the component in each of the ports, for both ports that is connected. Then from there we use, because we have used a Aspen property method embedded in the model, we can calculate the enthalpy of the ports, enthalpy of the stream that is leaving the port based on the temperature and the pressure of the stream that we have defined in the ports, and the mole fraction of those stream. Then to calculate the enthalpy, then we can do enthalpy balance to get the outlet's enthalpy. So if there is any increase in enthalpy in any of the stream, it will affect the output enthalpy balance. So these are just basic chemical engineering equation that have been implemented in Aspen Custom Modeler code. Then the last thing is to do the outlet connection, that is to transfer what we have calculated inside the model to the output port, so that we can connect it to another model. So, and since we are using a mole fraction plot, this can even be connected to any streams or any operation in Aspen Plus or Aspen ICs, because of the compatibility of the ports. So for the outlet connection, you have connection outlet F is the flow rate that will be leaving the outlet flow, will be equal to M flow. The Z will be equal to mass fraction, and you can see the enthalpy has already been connected. So we compile the model to check if there is any compilation error, if there is anything, and we check the message that will show us if there is any error in the model. So the error is actually in inlet 1, inlet 2. Okay, I think I made a mistake. The port is not input, it's supposed to be inlet. So at the end of the model, there are two ends. So I'm going to remove this one. So I think the code has been configured correctly. So we have the code here, the ports, the variables, the equations that guides the operation of the mixer. So this kind of mixer calculates the enthalpy of the outlet ports, the outlet stream. So from the enthalpy, we can calculate the temperature and the light. So the pressure, we can find the lowest pressure in the input for the pressure by calculating outlet just P is equal to main inlet, assuming no pressure drop, comma, inlet, give me a minute, inlet 2 dot P. So it's going to assume there is no pressure drop. Always make sure that there is a semicolon at the end of the code, part of the syntax for the language. So this is going to pick the minimum pressure that is defined as the pressure here. So the only thing left is the temperature that will be calculated. This will be calculated by calling the enthalpy of the product using the mole fraction and using the mole fraction of the outlets. So it's going to reverse calculate it. Outlet enthalpy by using the mole fraction outlet and the pressure that has been specified outlet outlet and the pressure that has been specified. So it will use the mole fraction and the pressure that has been specified to calculate the temperature, this outlet temperature. So we have all the variable of the outlet. So this is a standard mixer in any in Aspen and Aspen Plus and Aspen IC's simulation. So we can test the model by creating the model in the process flow sheet window. So you go to model, you copy the model from here. Okay, you pick the icon. So this is the model. Then I'm going to connect two streams to the model inlet port, two material streams to the model inlet ports, then one stream to the model outlet. So the first stream is going to contain 10 mole. Then the specification is variable that you are fixing and variable that you are freeing. A fixed variable is like input parameter that you specified in the model to solve the simulation. So you fix this, the flow rate of this, you leave the enthalpy. Let's fix the pressure. That one is easily known than the enthalpy. So let's fix the temperature and the composition of this stream. To know the amount of variable to fix, you use the specification status bar, and you can also analyze by using specification analysis tab to analyze some variable to fix and some variable to, you can see all these variable, they need to be fixed, so you can accept them. You understand? Instead of doing it manually, you can accept them, then it will fix all of them and your simulation will be squared. So you can now run the simulation and generate the result. So that's what I have done. You can see after I use my specification analysis too. So it assess me to fix some of the variables that are important. So, but it's not always right. But as you are starting, you can use those two for your simulation. So I'm going to make this one to be 0.1 and this one to be 0.9. Then I'm going to run. So once you see the run has completed, then the simulation is done. You can now see the results of your variable. So okay, so this is another inlet. So this is actually freed. You can see this is actually freed. So I think I can do it like this. Give me a minute. Instead of using simulation assistance, I can free the result here. I'll prefer to free the output and fix the inputs of the simulation, and I'm going to fix all these inputs. I'm going to fix this one too. Oh god, I'm going to fix this too. Then I'm going to fix the pressure here. I'm going to fix the pressure here. Then I can easily adjust this to be 0.8 and this to be 0.2 salt fraction. Then the other one, okay, this is 0.4 and this is 0.6 fraction. So, and I'll see the results in my outlet. Yeah, so here is the result in my outlet. The temperature, the 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 pressure is given. So if I adjust the temperature here to be 50, then I can run the simulation and generate another temperature here for the outlet temperature and the pressure. So that's how the simulation is done in Aspen Custom Modeler. So with that, we have created a custom mixer model that can be customized to any way that we want. Maybe if there is any special or modeling inside the custom, it can be incorporated inside the code and we can simulate the process with the powerful tool called Aspen Custom Modeler. So stay tuned to our channel. It's Abdurrahim Babatunde Popola. Thank you for your time. So if you have any topic that you want us to also do tutorial video, you can always send us an email on our email, which is nobera@gmail.com. So thank you. Stay tuned.